Okay, welcome everybody to week 2 of the 5-axis post-processing class from The Apprentice. This is day 1, this is our Tuesday, and section 1, so this very start of class on Tuesday. When we left off last week, we had gone through and configured a new post for a Cincinnati 5-axis gantry. I'm going to ask, before we get started with today's lesson, if there are any questions from the stuff that we covered last week. We did, by the way, do an office hours on Saturday. I know there was a little bit of mix-up about the time for some people. I'll make sure that I send out a reminder on Friday just to get everybody in the swing of things. It is a slightly different time, so just a reminder, class on Tuesday and Thursday is at 7:30 p.m. Eastern. It's 4:30 Pacific. And on Saturday, we meet at 3:30 p.m. Eastern, and that's 12:30 p.m. Pacific. So just a reminder on that. Not seeing anything come up on the chat, which is okay. To kind of recap what we did, we're following loosely the generic post guide PDF file that goes through all of the different settings inside the post. So we talked for a while about the basic vector settings. And for those of you that that weren't there, we also covered another, I guess, some extra information about using those vectors. We just kind of went over it in a little more detail and did some kind of practical examples of building the vector lines in Mastercam to kind of show visually and physically how these two perpendicular vectors end up creating a rotary axis mathematically. So we're using these two vectors that are always perpendicular to the actual axis of rotation. This, I guess, picture here does as good a job of any of showing that. For creating a C-axis that rotates around Z, here what we're showing is vec Y positive being the 0 location and vec X positive being the direction. So these are two perpendicular vectors, Y plus rotating towards X plus, and that plane forms our axis. So the axis is perpendicular to this plane. We're going to be doing the same thing when we configure for a Trunnion style machine, which we're going to start on Thursday. Today what we're going to do is go through a few more of the settings for setting up a gantry machine. So we've set M-type, which is kind of the global switch that tells Mastercam what type of machine it is. M-type 2 is head-head. It's a gantry style machine. So both rotary axes are on the spindle side, and in general with a machine like this, the part either stays stationary or it only moves with a linear axis. So maybe, you know, the table has an x-axis or even an x and y, but both rotaries are located on the head. We set the two axes of rotation using rot axis and rot direction variables. So we have rot axis 1, rot dir 1, and that's the primary, and we have rot axis 2 and rot dir 2, and that's the secondary. Once we get done setting that stuff, we went through and we set up our tool length. And what we're doing here is we are using tool length, and we're using the Mastercam overall length field. So we enter the actual pivot distance from the tip of the tool to the pivot point of the machine. And with this style of machine, the XYZ point that you see is always the pivot point of the machine. Even if we're doing what would normally be 3-axis work, the Z is always offset by the length of the tool. And that is so that we can program with these known tool lengths, and we can drive the machine in a 5-axis mode, and the XYZ code that we give the machine is what makes it cut the part. So there's no intelligence that's built in on the control side. In other words, the machine doesn't really know where the tip of that tool is. It knows where the pivot point of the machine is, and it knows the A and C or B and C or A and B angles that you're telling it to rotate to. And we've done the math inside the post processor to put the pivot point of the machine in the proper spot. Now, granted, this does lead to quite a few limitations, and it isn't until about 10, 15 years ago that control technology finally caught up, and they've added new functionality to the machines that allow you to do things like tool center point control. And that is basically dynamic length compensation in 5-axis mode. So you can actually enter a number, you tell it what the tool length is, and the machine itself already has the pivot distance. So from the gauge point on the spindle face back to the pivot point of the machine already has those numbers embedded in the control. In fact, it's usually set up by the applications engineer that comes and installs your machine. So we've got the length options turned on and set. Now we need to worry about setting up our rotary axis limits. So when you first start building the post processor, the first thing you're doing is always setting the vector directions. Don't set your rotary axis limits until after you make sure your rotary axis and rotary direction variables are set correctly. So the post has all of these options that are built into it to allow you to change the output of the code. But what I've found is that if you start to turn them on too early, you miss this. You miss the fundamental principle of setting up the rotary axes in their proper orientation with the proper 0 point and the proper direction. And so we'll do a little bit more looking at 0 positioning, because we're going to do some more testing on this 5-axis. And specifically, I recommend you set these values first before you turn on two things. There are some options here that change the way that the rotary axes are output. So 0 is normal angle output, so you get plus or minus whatever the rotary limit is. So if you've got, 3 rotations positive, you're going to get 1080. If you've got 2 rotations negative, you're going to get minus 720. And that will go up to whatever your limits are set to for the primary and secondary. So the first thing I recommend is that you make sure these variables here, P AUG output and S AUG output, are both set to 0. So they're both set to normal angle output when you're first testing. basically don't set these until the very end, until you've set everything else. Because again, these will, if you set this to implied shortest direction 0 to 360 and you make a 90-degree move negative, you're going to get positive 270. And so you don't want to turn this stuff on until you make sure you've set the rotary axis and rotary directions. The second thing I recommend you do is that you leave your angles set to these high limit values for both the primary and the secondary until after you've configured rotary axis 0, so rot axis, and rotor, so those sets of variables. Because again, in forcing the limits to be turned on will restrict the range of potential positions that your tool can get to. And sometimes by turning on the limits too early, it can give you a false, I guess, output when you're looking to see, are my rotary axis direction and angle settings correct? So once you get those other things set, that's when we want to come in and set the limits. And I recommend you get these set first before you go in and set P AUG output and S AUG output for the primary and secondary. Okay, so we're doing a Cincinnati 5-axis gantry. Let's get these set up. For our Cincinnati, we've got 200 degrees of travel. I don't think we need the decimal point. So on this machine, the C-axis can rotate plus or minus 200 degrees. We've got 400 degrees of total travel, but it's not plus 360, minus 40. Or is that right? Plus 360 minus 40, or vice versa. It is an angle range where you've got an equal amount of positive and negative travel, but neither one is over 360 degrees. They're actually just both over 180. So if you read the section in the 5-axis PDF about the limits, the rotary axis limits. Rotary axis limits must be applied to each rotary axis. The range of the limits, the toolpath, and the machine type determines how the post reacts when a limit is violated. Avoiding the limits is the best machining practice, but this is not always possible. The following slide is the section from the post where the limits are set at. It is important that the limits are set in degrees and that they are in terms of normal, unlimited wind-up output. Limits are resolved to these 4 types. So a rotary can have less than 180 degrees of total travel. It can have equal or greater than 180 and less than 360. It can have the soft limits at 0 to 360 with hard limits slightly beyond. And it can have a rotary limit that is greater than 360 degrees. Now, a lot of the machines that you set up that are allowed to rotate past 360, they'll either be one of 2 types. They will either be literally an unlimited rotary. In other words, you can do 50 million revolutions, and with every revolution it's going to go from 360 back to 0, and then 1, 2, 3, 4, and start counting up. And then there are some machines where there actually is some type of limit that's either hardware or software based. A lot of the times it'll be certain number of revolutions. This machine can do 27 and a half revolutions. This machine can do, 1,504 revolutions, and then after that, it's going to bind up. You need to know what those settings are so that you can set the actual number of rotations in the post. So if you look at your machine manual and it says, hey, this machine can do 65 revolutions plus or minus, you just whip out your calculator and it can do 23,400 degrees plus or minus. So for a rotary table or whatever, that's the limit, and those are the numbers you plug in. Now, there are two variables: primary limb type, secondary limb type. And you can set these to instruct the post which of those four rotary types you've got. There's also logic that was added a little later, and by little later I mean, from version 9 to version 9.13 or something like that. This is still way back in the day. They added a switch that is auto set the limit type. So when auto set limb is turned on, is set to 1, we essentially ignore these two variables here, and MP will look at your primary limits and your secondary limit settings, and it will automatically figure out pri limb type and secondary limb type for you. So that's what that auto set limit does. It allows the post to examine the limit entries and automatically set the limit type variables. And it just says leave this enabled. So before, you had to worry about setting these two. Now you really don't. The post will do that for you, and all you really need to worry about is setting the actual limit values. So when you're looking at the rotary limit types, less than 180 degrees, that's when the total rotary axis travel. And when we say total, what we mean is we're going to add up both the positive and the negative rotation. You may have 110 degrees positive, but if you've got 90 degrees negative, that adds up to over 180 degrees. So you just have to look at what you've got. For the limit types where they're beyond 180 but less than 360, you might have something like this. 0 is the low limit, with 225 being the high limit. When you have, so let's get back to this. When you have a rotary limit type less than 180, both the actual limits, which is primary limb low and primary limb high, are set to the same angles as the intermediate angles. So when you look at these sets of values here, primary limb low is the low limit. Primary limb high is the high limit. Primary int low is the intermediate angle. In other words, when we pass this angle, as we approach this value, we're going to set a flag. We're going to trip a limit inside the post. And this is to allow the post to sense whether we are about to pass that limit or not. And in those cases, it triggers some stuff internally. So let's look back here. When it's less than 180, we set the primary, or we set the low and high limits and the int values the same. So you can see 0 and 110, 0 and 110. And this is the absolute angles for travel, and this is the intermediate angle. So they're both set the same. That statement is also true when the total travel is between 180 and 360. So the values for the limits are set to 0 and 225 here. The values for the intermediate are set equal, 0 and 225. When we get to the other types, so there are 4 types. There's 0 to 180. There's 180 to 360. This is type 3, where we have soft limits at 0 to 360 with hard limits slightly beyond. So the rotary axis travel is normally 360 degrees, but the rotary axis can exceed the travel by a small amount. The intermediate angle is set at the normal travel, and the axis travel is set to the maximum limits. So here's a case where we have 0 to 360 set for the intermediate angle, and you notice we've got -5 and 365 set for the absolute total travel. Now, our situation here with the C-axis on the Cincinnati is very similar to this. Because really, we've only got 400 degrees of travel. We've only got plus or minus 20 extra degrees beyond a 360-degree circle. So we're probably going to adjust these intermediate angles here. The 4th type is greater than 360. And this is where the axis travel is allowed to wind up. So we can go past 360, and we may only be able to go positive. So in that case, it would be low limit would be 0, primary limit would be 360 times however many revolutions we can go. If your rotary axis is truly unlimited, then I would put something like 7 nines in there. So this is 4 nines. I can't remember what the limit is. It might be 9 nines. But you can certainly put that in, again, if your axis truly is unlimited. So getting back to this rotary type here. So what I'm doing here is I'm setting an intermediate angle. So if the post trips that intermediate angle, then it will attempt to reposition. There are a couple of different routines inside the post processor. I shouldn't say a couple. There are many routines inside the post processor when it comes to using limits and whether or not the limit is on the primary or on the secondary, and what do we do when we violate that limit. Typically what we're going to do on a gantry, we are going to realize that we tripped the limit. We are going to retract the tool along the tool axis vector to a safe position. We're going to unwind the head. We're going to reposition to the same angle that we were at, but with the C-axis rotated 180 degrees, and the A-axis or B-axis rotated the opposite way, and then we're going to reapproach the part and attempt to continue the cut. Typically when that happens, it does leave a mark on the part, a little bit of a gouge mark where, you know, we started the cut and stopped the old cut and started the new cut. So if at all possible, we want to avoid hitting that limit. So sometimes we actually have to, drive the toolpath, post out the code, and then look at the code, scan through it to see, is there a reposition move or not. Most of the time when you do hit that limit, you will at least get the warning of a post prompt will pop up and let you know that something happened. let's take a look at this. Secondary limit thing on this one is 95. It's either 95 or 100. Set it to 95 for now. Bias null. When we are dealing with these limits, we have some options in the post that allow us some control. So in the miscellaneous integers, we have miscellaneous integer number 4 and miscellaneous integer number 5. And they're basically identical. Miscellaneous integer 4 applies to the primary. Miscellaneous integer 5 applies to the secondary. And we have a couple of options. 0 is off, which essentially just uses the default post positioning. Minus 999 says try and set the primary to the low limit. And with the primary at the low limit, attempt the cut and then see if the secondary can be put into a valid range. Positive 999 says do the opposite, go to the high side. So put the primary axis at the high starting point and see if we can calculate a secondary that's in the range. Any non-zero value from basically plus or minus whatever the total travel limit is means attempt to position the primary at that angle. So if you want to try and start with the primary positioned at 90 degrees or 80, whatever you want it to be, you can enter that value in here. And the post will attempt to use that value. Now, there are some things that kind of matter, right? You can try to bias the primary, but it's unless you know that the machine can achieve that starting position, the best solution really is to start with them set to 0, post out the code and look at it, see where the post is attempting to go for the first couple of moves, and then come back in here and adjust these if you need to. Very rarely do we start off and just know, oh yeah, we're going to bias this thing right from the get-go. Most of the time, it is a series of, making a cut on the part, looking at the code, seeing if it's what you expect it to look like, and then coming back in and making adjustments as needed when you do need that control. All right, so let's take a look at this. Bias null tells the post whether or not the MI4 and MI5 bias values get applied at the null tool changes. Okay, so if you're using the same tool in separate operations, by default, the MI4 and MI5 bias settings do not get applied in the null tool change operations. So if you want to be able to apply that, you do need to set that to 1. So here's a case where we've got 190 total degrees of travel on the secondary axis. Let's do this to our secondary. because what I want is I want you guys to see an example of tripping the limit. So here's a case where, let me do this too. I'm going to bump those values up a little. Okay, so we've got minus 30, we've got positive 110. We're going to save that. Okay. So I've got a tool path here where we've got a hemisphere. And if we look at the toolpath type, we're doing a project curve. Got a 3/8 ball mill. And under the cut pattern, I'm projecting this curve down onto the part. And we are doing a surface normal projection. So as we step across the part using our cut tolerance value, which is a quartile tolerance, every position along the line gets projected down using the normal of the surface itself as the projection. That's why we start down here close to the bottom and we go all the way over. So if we backplot and we look at this, what this path looks like, we're approaching the part. Okay, we're cutting all the way up to the top, then back down along the bottom, and we retract. And everything looks good, but we've definitely got more than 140 degrees of travel. I think that's what we told it we could do. Part of what we also need to be aware of is, where is that travel range, right? 110 degrees is great, but this tool doesn't drop down past 90. So part of our positive range is limited, and then there's a big section where we go past that negative 30 degrees and we're kind of stuck. So if I post this out with our 5-axis gantry, we get a notice, right? We get an error message. The tool cannot be positioned within the machine rotary limits. So here we've attempted to do a bias here. We've started at C180. We've gone to B100. And you can see that here, B101, B103, B106, B108. So it looks like that B value is just increasing. We can have a couple of things going on in a situation like this. First, we can try to reverse the actual direction that we're traveling across the part. So if I take all this geometry and rotate it, or we go back into project curves, come on, and we go to the projection curve and we reverse it. So that can be one test that we want to do when we're setting up a 5-axis like this. So if we reverse that direction, see what we get. At least it starts at 0 now. But you notice it's still trying to go up. Okay? Well, that being the case, we can go back in here and we can try reversing them. Well, let's see what happens if we go both directions here. So I'm going to give it more travel. It's kind of strange there. P100. Oh, you know what it is. Okay. I know exactly what it is. The problem is the range that it's trying to find for these vectors, and I've got my rotary axis direction upside down. So this 0 should be pointing straight up, not straight down. And we'll still try the positive vec x. That was my entire problem. So, great example of where having your vector directions not correctly configured, it doesn't matter what I put in for that rotary limit. It was basically 180 degrees out of phase on my secondary. Now you can see this is making a lot more sense, right? 79 degrees. We look at that. Okay. You know, if I'm looking at the front of there and I'm looking at this angle 79, yeah, I'd buy that as 79 degrees. And now that my vector direction is correct, I should successfully be able to do this. There. So we repost. And let's see what happens. We start at 0 and 79 degrees. We are moving in X, Z, and B, and we're using inverse time, which means that each of these F values here is a time value. Okay, it's the inverse of the amount of time it takes. The bigger the number, the slower the move, which is really unintuitive. If you get an F that's like 0.0002 or something like that, beware. That means it's a really, really quick move. And look at our B. So our B is decreasing. We start at 79.5 and we start decreasing 40, 30, 20, and eventually we're going to cross over. So here's where we cross over at B0. Now we start going negative. And this is exactly what happens when we hit the limit. So we hit this limit at 29.633 degrees. The next move, the post goes and does its calculations and it sees, oh, okay, I'm going to violate the part. So what's it do? It retracts along the tool axis vector. So you can see we've got a negative X and a positive Z move. The previous X was negative 3 something. The new one is minus 7. So it's going to go about 4 inches over an X. And Z goes from, 5.6482 to 12 something. So it's going to make this angled retract move. Basically, along the tool axis vector that it was at, it's going to retract. Then it's going to unwind the head. So here it's doing the unwind move. Now it reapproaches back to that same point. So here, 3.2168, 5.6482, and you'll see 32168, 5.6482. So it reapproaches in feed, and then it continues on its merry way because we've rotated the C-axis 180 degrees. Okay, and it finishes the cut. Yeah, and it flipped B. Exactly. So if you look at where B was negative, B is now positive. Okay, so we need to make sure that it's retracting far enough that we're going to clear the part when we do that unwind move. So to make sure that it will clear, if you go into your additional settings, miscellaneous values, this is the clearance that it's using. This value here for miscellaneous reel number 1. Retract and approach clearance distance. If I tell it 20 inches, you can see there's our 20-inch move. We've retracted 20 inches off the part, we've unwound, and we've reapproached. If I go back in there, now remember, when it does its unwind move, it's just moving those rotaries at rapid. So it just goes C180, B whatever. So it's not holding that tool point stationary like tool center point control and moving the machine around that tip, the pivot point of the tip of your tool. It's just moving or B and C or A and C regardless. So you need to make sure you give it enough room. And I think the default is like a 2-inch or like 50 millimeter retract. So that may not be close enough. So just fair warning, that default value is pretty small. So here, we're only making like a 2-inch retract move, then unwinding, then reapproaching. By the way, save that before it crashes on me. Let's do that. Give it a nice fresh restart, fresh set of electrons. So this unwind example kind of clearly shows why it's a good idea to have a couple different test scenarios. Because last time I set up, I was just looking at, a couple of positions that we were moving to, and I didn't notice that the negative vec z was throwing off our output so bad. Alright, let's do this. Okay, so if we look at this path, we're approaching the part, and we're just spinning around. Got a good question. Will any of the simulations show the retract? No. None of the default simulators, and that is both Verify and Machine Simulation, will show you that. You'd have to get some. There are two situations where that's not true. If you purchase a third-party verification system like Vericut, NC Simul, or iCam, they will read the NC code and they will perform a real simulation based on that NC code. The second time when the Mastercam simulator will actually show you the correct move, it is now possible to integrate the 5-axis post processor and the Mastercam machine simulator. It still doesn't verify actual G code, but what ends up happening is the same post that outputs all of the vector moves. So when we look at this, for example, when we have a post that actually outputs these vector moves, including the unwind, it is possible to link the post processor and the simulator together so that the simulator runs off of intermediate code that is actually created by the post processor. Now, in order to get that to happen, you've got to pay for somebody to hook up the Mastercam simulator to the post processor. Currently, the only people that are doing that are third-party post developers, and that would be Postability and in-house solutions. The reason that it is so limited as to the companies that will provide that as a service kind of has to do with the way that CNC Software and Module Works struck their partnership together. So part of the deal is that Module Works has created this programming interface to the machine simulator. And they want users to pay a fee, a royalty fee, to be able to use that that application programming interface, that API. And both in-house solutions and Postability have entered into an agreement with with ModuleWorks to allow them to provide the service of integrating the simulation and the post processor. When I looked into doing that, the fee was approximately 50%. So if I were to go out and integrate a post for somebody and hook up that post to the machine simulation, and I charge the customer $3,000, ModuleWorks would want $1,500 of that for the privilege of doing it. So it is possible to pay somebody to hook up your machine simulation to your post processor. And what you end up getting is a decent solution for 5-axis simulation. It's still not the same thing as Vericut or NC Simul. I mean, Vericut and NC Simul are the best of the best when it comes to dissecting NC code and interpreting that into machine motion and showing you what's going to happen on the real machine. But it's also like 10 times the price. So you kind of have to balance that with, how many high-end machines do you have, and do you need the capabilities of Vericut versus the cost. So, you're going to be looking at roughly, $18,000 for Vericut, kind of on the cheap end, up to $35,000 with it fully configured. Whereas hooking up the 5-axis post to the ModuleWorks machine simulator is going to run you like a tenth of that. It's going to run you like $3,000. But it's still not guaranteed to catch everything. It'll catch almost everything. The devil's always in the details. That's the unfortunate part. So, I think for the money, getting somebody to hook up a post so that it works with machine simulation is pretty cost effective, honestly. And a lot of it really depends as well on how much full 5-axis motion do you guys cut on a daily basis. Out in the real world, kind of, when I'm driving 5-axis, 90% of what I do is 3+2. It's the pretty rare part where we actually need full 5-axis motion. Now, maybe not. Maybe you guys have You're doing aerospace and you've got pockets with tapered walls and undercut stuff, and you're doing it all day long. At that point, what's more cost effective? A solution that works 98% of the time. That 2% could be a spindle, and that's the problem. Is that when you really need machine simulation, you really need good machine simulation that's accurate. So really, that there is this kind of mid-priced option now where you can hook up the post to the machine simulation. Now, I should put an asterisk on that statement. I should put a little caveat in there. When you pay to have the post hooked up to machine simulation, that's an add-on charge on top of the regular cost of the post. So you're not going to get in-house solutions or post ability to take the generic Fanuc 5x mil post that you configured and just add machine simulation to it. They won't do it. They're going to want to sell you a post for your machine and then have the fee of hooking up machine simulation on top of the cost of the post. Yeah, I mean, it is what it is. It's unfortunately ModuleWorks and CNC Software did not work out partnership details that give us, the end users, access to hooking up machine simulation to a post processor directly. It would have been nice if they had. But yeah, unfortunately, well, maybe the market will demand it. But the more people that get into doing high-end 5-axis work, honestly, you're stupid if you don't have something like Vericut or NC Simul. And I don't mean that to be insulting. I just mean that as you get into having more complex, high-end 5-axis machines, the software pays for itself in terms of, number one, productivity. Because now you're not dry running these programs out on the machine and having the operator, take 2 days to get through a part. And there are some additional functionality like OptiPath. So some of the functionality that's in Vericut to allow you to optimize your programs by detecting, how much engagement of your cutter is happening and allowing it to actually vary the feed rate throughout the program, and also do things like speed up the air cutting. So it'll actually analyze where your tool's at when it's in the material, and if you've got, a half-inch move at 2 inches a minute, but it only contacts material for the last 100 thou, well, Vericut's gonna do the first 300 thousandths at 150 inches a minute and then slow down. Complete is another one. Wing brought that up. It's decent. My big complaint about Complete is that it was originally created only for Matsuras. So for the first, 5 or 10 years, the only thing that it supported was Matsura. And now they've just added a couple more machine types to it. How can I say this? I prefer to have computer-aided verification software that supports a broader range of machines on the market. So I don't know if they do turning yet. I know that they weren't doing turning for a long time. I think they finally just added turning to it. But Vericut will support really any type of machine that you could possibly imagine. A lathe, a mill turn, a robot, a freaking mill turn with a robot. It'll show, you can program a pallet pool, and you can watch the pieces move down and the pallet shuttle in and out. You can program just about anything. So, I mean, they've got some specialty software now, and they're the only ones in the world that are doing programming and simulation for fiber placement machines. So they've got, a partnership with Electro Impact and with a couple of other companies that build fiber placement machines, and they've got the software to program and simulate laying down, basically what you can think of as rags or strips of cloth. I mean, it's carbon fiber, but mathematically that's what they end up doing is laying these little ribbons and strips to build up the part layer by layer. So NC Simul, is kind of the same way. It'll support very complex mill turn machines. NC Simul's got a really cool thing now where they have an internal translator that will translate a program from any type of machine to another type. So if you've got a 4-axis vertical program that uses an A rotary and you want to translate it to a horizontal machining center, you can just move the part from one machining center to the other, and using the kinematics of the machine and the envelopes of interference when it rotates the parts and the fixtures, it will automatically reprogram all of the retract and approach motion for you. So for those places where, and I've worked at them, for those places where they can never make up their mind, and one day they want you to run something on a vertical and the next they want you to go to a horizontal, and they can, they want to be able to move stuff around randomly and quickly, it's an awesome tool. I mean, absolutely awesome to be able to, take a part that is programmed and just move it onto a machine with a completely different kinematic configuration and just tell the software to figure out how to make it work, and it does it. So, all of the softwares have their pluses and minuses, and I would love to see the machine simulation in Mastercam get cheaper and easier to use. I just wouldn't want to sacrifice the peace of mind that Vericut gives me. The last one I mentioned was NC Simul. It's a French company, and honestly, they're pretty aggressive at getting into the U.S. market. The other thing about NC Simul that's pretty sweet is you can really beat them up on price. So I've heard of people coming in with a $30,000 Vericut quote and browbeating the NC Simul guy, and they're walking out of there with a full-fledged software package for $3,000. So NC Simul will really be open to heavily discounting the price of their software. The question is always, what does it take to get your machines configured in the software? Are you going to be able to do it yourself? I mean, obviously they have training, but who's going to be responsible for setting up the machines and making sure the machine is configured to accurately simulate the G code and the M codes? Whatever code you're throwing at the machine, somebody's got to set it up and make it all work. So all of those computer-aided verification packages are worth the money if you're willing to spend it. And they all have their pros and cons to them as well. Oh, okay. Sorry for getting a little sidetracked there, but I think it was a good discussion. We're going to go ahead and break the video and take our mid-class break. So it's like 37 after the hour. We'll come back at like 50, 52 minutes. So we'll take about a 15-minute break, and then we'll get started.